So the brief I've received, as I understand it, is to give sort of an overview and progress report of the science we've been doing in the Livermore Goddard Lab Astro group. This is a product of work from a very large collaboration of people. I'm going to apologize in advance. This is a little bit of a Frankenstein talk where I've stolen slides from a number of people's contributing talks. I'm going to try to cover a lot of ground here, several different topics. So let me first give you an overview of the facility for anyone who's not familiar with it. This is the Lawrence Livermore EBIT facility. It's the original first EBIT. And this is showing it with a suite of different spectrometers. Here is the NASA Goddard EBIT calorimeter spectrometer, which I'll talk about more in a moment. This right here is a high resolution grading spectrometer. This is an example of high resolution crystal spectrometer. Here you can see high purity germanium detector, and there's a very large suite of available instruments to study with. Just briefly, a general property of EBITs is that you're producing a monoenergetic electron beam with some relatively narrow width, also spatially narrow. You can access a wide range of electron beam energies to produce a wide range of charge states for study. Electron densities are moderate, and by varying the beam energy, you can interrogate different processes. You can also do simulations of things that are relevant to astrophysics by making a quasi-Maxwellian. I'm going to skip this slide. This is an image of the detector array of the EBIT calorimeter spectrometer. The sensor array itself is very similar to Hitomi SXS or CRISM Resolve. One important difference is that you can see half of the array has much thicker absorbers, which gives you a larger energy bandwidth at the expense of energy resolution. This is the next generation calorimeter spectrometer that's going to be deployed at Livermore. It is a transition edge sensor array. This is a prototype Athena technology. This is a kilopixel array with a quarter of the pixels being read out. And the cryogenic package is similar to that's in the ECS. It is, however, a cryogen-free cryostat. So it'll be able to run continuously. These are some of the first results which are being used to validate the Athena array design for Athena, showing that we're getting 2 eV resolution at 6K eV and in compliance with the Athena requirements. This is really exciting results from Steve Smith et al. Okay, so now let's get to some of the atomic physics and astrophysics. So I think you may have seen this before. This is from our atomic physics paper from Hitomi, showing the contributions of different processes to forming the resonance line and forbidden line of helium-like iron. This is showing some of the outstanding discrepancies at the time of the writing of that paper between the models and the data, between the models and each other. And so you would like to interrogate the line formation processes here to understand what is actually correct in the models. Let me just take a step back. So Chintan was showing that there were problems with the atomic structure of iron 17. So you can ask, well, is it okay for helium-like ions? Because certainly we want to get the atomic structure correct first. And the best test so far is this natural line width measurement of helium-like iron resonance line. And the experimental precision of this is 3%, which is really an experimental tour de force. And the theory actually agrees with these measurements. So yes, actually for helium-like ions, we can get the wave functions correct. Okay, so now how do you want to actually accurately benchmark the K-shell line strengths? So you want to get absolute cross sections by normalizing the radiative recombination peaks. You want to measure the polarization because you have to account for the anisotropy of the experiment. And then you want to measure with different charge balance conditions so you can disentangle contributions from direct excitation and intershell ionization. So radiative recombination, let me remind you, is when you have a free electron that goes into a bound state and emits a photon. And the idea is that theory should be able to get the cross-section for this more accurate because it only involves one bound state, whereas direct excitation involves going from one bound state to another bound state. So you have to worry about the overlap of two bound state wave functions. And so if you know this cross-section of the radiative recombination accurately, then by taking the measured line ratio, you get the cross-section of the direct excitation process. And just to remind you, this is what radiative recombination continua look like in astrophysics. They're continua because these electrons have a Maxwellian distribution in astrophysics, but in an EBIT, they're monoenergetic, and so you get a series of lines. And so this is an example of a spectrum that you could measure for iron K with an EBIT, and here you have all of the strong lines of hydrogen-like, helium-like, and lower charge states. Here you have recombination into the n=1 shell, into the n=2 shell, and n=3 shell. And you need these thick absorbers that give you a large bandpass to get up to these high energies. Here you can see in red, these are the high resolution pixels that have a SXS or a Prism Resolve-like resolution. And then the blue spectrum, these are the lower resolution high energy pixels that give you these radiative recombination peaks. And so here are some of the preliminary results. This is being led by Natalie Hell. So this is showing Natalie's measurements for different, the light blue is relatively more lithium-like, and the dark blue is relatively less lithium-like, but for the same electron beam energy or beam energies here. And then here are theoretical calculations, and the largest remaining contributions to the uncertainty in the measurements are the counting statistics in the radiative recombination peak, which you can see here are much weaker, of course, than the actual strong lines, the K alpha complex, and then of course the uncertainty in the polarization, which I'll come back to in a moment. This is showing some preliminary results for the forbidden line. Again, this is when you have a lot of contribution from inner shell, from lithium-like, and this is these measurements are with less lithium-like, and these two branches are the corresponding calculations that are including all the relevant processes. Here is another example of similar measurements for K-shell sulfur. This is being led by Chintan Shah. Here you can see also the polarization measurements that are being done. This is the two different polarizations, and then this is the degree of polarization resulting from these measurements. Okay, now let's move back to the L shell. This is what the same topic that Chintan was just discussing. So one other way of probing this discrepancy between theory and the line strength, which was measured by Greg in 2006, and then also probed by these structure measurements that Chintan was showing. You can also make the same measurement as a function of atomic number, which could show you first of all, that you didn't make a mistake in a given measurement, that essentially it's reproducible, but also it can show you the scaling of the problem with atomic number. And so this is, again, some preliminary results that Greg Brown and Tom Lockard have made and are preparing for publication, showing that the problem in the 3C line does indeed exist for neon like nickel as well. Okay, now I'm going to show you some results on dielectronic satellite transitions. So this is using a high resolution crystal spectrometer. So here you can see n=3, n=4, n=5 spectator electrons, and greater than 5. And so important results that come out of this are that all of the dielectronic satellite lines are associated with the 3C and 3D. There's none that are significant that are associated with 3F, 3G, M2, which are these are the 2p to 3s lines. And this is a result that those lab results speak to. This is actually done using Capella and Procyon. This is using the n=4 spectator satellite lines to constrain the temperature. And here you can see a quite precise measurement from Capella. And this is actually a really neat result. This constraint for Procyon is made using, if I remember correctly, something like 3 or 4 photons. In that spectral bandpass, the background is low enough that you can actually make a measurement like this. Okay, now you can sweep the electron beam to simulate a real astrophysical plasma and get all of the relevant processes involved. Here, this is this famous detection of a feature at 3.5 keV. One of the possible proposed explanations was satellite transitions that are not adequately accounted for in the databases. So this was led by Ezra Bulbul. This is showing here that there are there is some missing line flux that was not in the databases here. The blue line is the measurement here. But it's still not enough to explain the 3.5 keV line detection. Okay, here is a sort of demonstration experiment showing how we might study recombining plasmas and supernova remnants. So basically, you have a high energy electron beam to precondition with a high charge state, and then you switch to a low temperature simulation. So this is monoenergetic to make a high charge state, and this is quasi-Maxwellian here. You're sweeping the electron beam energy rapidly. And so here you can see this is the charge balance of hydrogen-like over helium-like. It's going up, and then as you hit your peak, then you switch to this sweep mode, and it starts recombining. And this is being led by Makoto Sawada, and he and Natalie have an APRA grant that they've gotten to go beyond the prototype stage and actually do a systematic study with this. Okay, here's another neat result. This is led by Tusita Artanayaka. It's doing density diagnostic benchmarks in the soft X-ray / EUV. This is a particular example of iron 12, which is a very strong and well-known diagnostic that's used for studying the solar corona. And you can see that the measurements they made here show that there's some discrepancies in the intensity ratio, although the sense of the scaling seems to be okay. This is a really neat technique. So basically the trick here is you have to actually get an estimate of the electron density. And the way you do this is by imaging the size of the electron beam in the ion cloud.
3 minutes, Maurice.
Excellent, thank you. Okay, and so the last thing that I wanted to show you is some charge exchange spectra. So these are results from Gabrielle Betancourt-Martinez PhD thesis. So this is showing L-shell charge exchange spectra. So this is fluorine-like nickel-19 plus recombining to neon-like. And here the blue is with molecular hydrogen, and the red is with atomic helium. And you can see these small insets are actually the full spectrum. So it's dominated by the M2 3G blend, although it's really basically mostly the M2 line, the forbidden line, which is the lowest lying excited state. For comparison, this is the same spectrum in direct excitation, electron impact excitation. And the reason that these are insets is so that you can see all of the details in the other small lines that are here. So you can compare this to theory, and you can see that for both what's in ACX, this is ACX1, not ACX2, and specs, at the time we made the comparison, the agreement isn't great. There's a number of problems both with the 3 to 2 line intensities, but also with the high N transitions as well, which are characteristic of charge exchange. And so I think we need to do some homework here to clarify what assumptions are going into these model spectra. We also have preliminary data from the iron L shell, and the top level result is that it's very similar to the nickel results. We have strong M2 and strong high in emission, um, and similar problems with the ACX and SPECS models. All right, so overview summary, we're making progress on benchmark measurements in a large number of different problems in astrophysics. We're mainly being motivated right now by needs for CRISM and Athena, and we do need new experimental capabilities beyond what we already have, and we are developing them, including the TEMS. And I just thought I would add one specific thing that we need to move beyond the charge exchange measurements that I just showed is we need measurements with calorimeter and an ion beam line so that we can do collision velocity dependent measurements of charge exchange. And that's something that is upcoming in a collaboration between Livermore Goddard and Clemson University. All right, thank you.
Wonderful, thanks very much. And so we'll take questions either via the Slack or the Zoom. I'll ask a question about that very last topic you made. Where are you going to get an ion beam? Is that going to come at Clemson or?
Yes, correct.
Using their EBIT?
Yes, I believe so, yeah.
Uh-huh.
I could also actually add that Auburn is providing a cold trims diagnostic to be complementary to the calorimeter.
Ah, wonderful.
Yes, it will be.